Tonight, you might crack an egg into a hot pan. In about 3 minutes, something clear and slippery will turn solid and white, and you'll flip it without thinking about it once. That change feels like the most permanent thing in your kitchen. In fact, we built a whole phrase around it. You can't unboil an egg. People say it when they mean something is finished forever. A decision you can't take back. A word you can't unsay. But in 2015, a team of chemists in California and Australia took a hard-boiled egg white, ran it through a machine, and turned it back into a raw one. They won a prize for it, and the reason it worked says something genuinely unsettling about everything else we've filed away as permanent. To understand what they did, you need to know what an egg white actually is. It's about 90% water. Almost all of the rest is protein. And a protein is not a blob, it's a chain. A long string of smaller molecules called amino acids linked in a specific order and then folded up into a very specific three-dimensional shape. That shape is everything. A protein shape is what lets it do its job. Grab another molecule, cut something, carry something, change the shape, and the job stops. In raw egg white, each of those protein molecules is folded up tight and compact, like a pair of headphones wound neatly, and they drift around in the water separately, not touching. Light slips right between them. That's the only reason raw egg white is see-through. Now here's the part almost everyone gets wrong. When you boil an egg, you are not destroying anything. Not one single link in those amino acid chains gets broken. Every atom that was in that egg is still there, in exactly the same order when you're done. What heat does is much simpler. It makes the molecules vibrate harder and harder until the neat little folds shake loose. The chains unravel and sprawl out, and once they're sprawled out, they run into their neighbors, and they snag. Thousands of unfolded chains catch on each other and lock together into a solid mesh. That mesh is dense enough to scatter light, which is why it turns white, and rigid enough to hold a shape, which is why it turns solid. Scientists call this denaturation, but the honest word for it is tangling. Your breakfast didn't transform, it got knotted. Which brings us to a chemist named Christian Anfinsen. In the 1950s and 60s, working at the National Institutes of Health, Anfinsen ran an experiment that sounds almost too simple to matter. He took a protein called ribonuclease and unfolded it completely with chemicals. Then he took the chemicals away, and the protein folded itself back up, not roughly, exactly, into the same working shape it had before, all on its own, with no machine, no template, and nobody telling it what to do. That result was so important, it won the Nobel Prize in Chemistry in 1972, and it's now called Anfinsen's dogma. Everything a protein needs to know about its own shape is already written into the order of its amino acids. Give it the right conditions, and it doesn't need to be rebuilt. It rebuilds itself. But that answer created a much stranger problem. In 1969, a biologist named Cyrus Leventhal did the math on what that folding actually requires. Take a small protein, just 100 amino acids. Give each one only 3 possible positions, which is a wild underestimate. The number of shapes that chain could take is 3 to the 100th power. That's a 5 followed by 47 zeros. If the protein tried them one at a time, at the fastest speed molecules can physically move, finding the right one would take about 10 to the 27th years. The universe is around 14 billion years old. The protein would need to search for longer than the universe has existed, many, many times over. And yet, in your body, right now, proteins are finding their correct shape in less than 1,000th of a second. This is called Leventhal's paradox, and the resolution is beautiful. Proteins don't search. The energy landscape they're folding through is shaped like a funnel, and they simply fall down it. There's no hunting involved. There's just a slope and one bottom. So here's the obvious question. If proteins fold themselves, and heat only unfolds them, why doesn't a boiled egg just quietly turn clear again as it cools on your counter? Because the problem isn't the folding, it's the company. A lone protein in water will find its way home just fine. But in a boiled egg, the unfolded chains aren't alone. They're welded into a crowd, snagged on thousands of neighbors at once. Before any of them can fold, they have to be pulled apart from each other first. And chemists have known how to do that for decades. The trouble was the method. You dilute the tangled mess enormously, add the right chemicals, and then you wait. Days, sometimes longer. For a laboratory, that's tedious. For an industry, it's a fortune, which is where 2 researchers come in. Gregory Weiss, a professor of chemistry at the University of California, Irvine, and Colin Raston, at Flinders University in South Australia. Weiss had the protein problem. Raston had built something odd, a device called a vortex fluid device, a thin glass tube that spins liquid so fast the fluid climbs the walls into a film only microns thick, where it gets sheared and stretched by the spinning. So they tried it on the least serious test subject imaginable. They took egg white, boiled it for 20 minutes at 90 degrees Celsius, a genuinely hard-boiled egg, and added urea to break the tangled mesh back into liquid. Then they poured it into the spinning tube. The shear forces did the untangling mechanically, ripping the chains apart from each other so they could finally fall back down their funnels. And the protein came back, not in days, in minutes. Their paper, published in the journal Chem Biochem in January 2015, reported refolding thousands of times faster than the old way. That September, the team was awarded the Ig Nobel Prize in Chemistry, the award for research that first makes you laugh and then makes you think. Their citation read, "For inventing a chemical recipe to partially unboil an egg." And the laughing part is obvious. Here's the thinking part. A huge amount of modern medicine is made of proteins, including the antibodies used to treat cancer. Making them is expensive, and the reason is exactly the egg problem. If you grow proteins in cheap, fast bacteria, a large fraction of them come out tangled and useless. So manufacturers use slow, costly hamster ovary cells instead just to get the folding right. Untangling proteins quickly and cheaply would change that math in an industry worth around $160 billion. The egg was never the point. The egg was the demo. And I want to be precise here, because the headlines weren't. They did not unboil a whole egg. They recovered one particular protein, lysozyme, partially from the white. Nobody turned a hard-boiled egg back into something you'd want on toast. But the principle is the part that matters. Because compare an egg to a log in a fireplace. When wood burns, chemical bonds genuinely break. Atoms get rearranged into entirely new molecules and float away as gas and smoke. There is no arrangement of machines that reassembles that log, because the log's ingredients are no longer in the room. That is irreversible in the real, physical sense of the word. The egg was never like that. Every ingredient stayed exactly where it was, in exactly the right order, the entire time. All that changed was the shape, and a knot is only a shape. Knots can be undone if you know which end to pull. So tomorrow, when you crack an egg into a pan and watch it go white, you'll be watching something that isn't destruction at all. It's a few trillion tiny knots pulling tight, all at once. Nothing lost, nothing broken, just tangled. The phrase survived for centuries because it sounded obvious. You can't unboil an egg. It was never a law of nature. It was a difficulty, and eventually, somebody with a spinning glass tube got bored of it. Which leaves the question worth taking with you. How many other things have you quietly filed under permanent? A habit, a mistake, a thing you said, that were never broken at all, just knotted and waiting for somebody to figure out which end to pull.